Okay, so at this point I've already recorded data from my observation session out in rural area for my interferometry project, and I'm back home now with all my data in hand in my computer, which you can see over here. So I have solid state drives, 3 different solid state drives. I have the east antenna's data, the north antenna's data, and the west antenna's data here in those 3 files there. So now the next thing that needs to be done to develop some correlation, some fringes from this data, is to align data from the 3 different data streams. So each of these files are really big. They're 800 gigabytes. There's 100 billion samples in each one, so they're pretty big. So how do you align the things together? That's where it comes down to a program that I've written called Triple Align SSD. So what does this program do? Well, it selects data streams from the 3 radios, which you can see right here. So it's going to point off to those files in the solid state drive. And then I can apply signal delays to the east stream, which is E raw, W raw is the west stream, and there's also the north stream, N raw. And this is the part that's empirical. These numbers are what, and I've already done the hard work of finding those numbers, but how did I get to that point? And that's what this program can help me do. So what I can do is I can change the numbers in here, and I've got this program set. So what it's going to do is it's going to read data from all 3 data streams, but it's only going to compare 2 different baselines. Down here I've got the east baseline times the west baseline, so it's the NP conjugate of the west. So this is going to produce a correlation product right here, this part. And I've set it up so that, for instance, the west channel will move 1 sample ahead of the other streams, and I found that this is the best way to align data, is to do iterative looks at data and then let one of the data streams slip ahead by 1 notch and see where that point is. So I know that's probably a little unclear, but let me explain a little bit more about what I'm doing. So I've got the west stream so that it moves ahead by 1 sample every time, and then I load up everything, all data from all 3 antennas, and then I do Fourier transforms from all 3. But I'm only comparing 2 of the, only 1 baseline at a time. And once I do the cross correlation here, so this is the east antenna's data times the conjugate of the west, that's the cross correlation right there. Then after that I do an inverse Fourier transform of this, which is shown right here, and that's going to tell me what the delay is. It's going to give me the delay between the 2 antennas. So if they match up perfectly, there would be a delay right in the center. So let me go ahead and just run this program and show you what it's going to do. It's going to tell me where the maximum is and how much energy is in that maximum point. And as the data slips along, you can see that the point where data is at its maximum is rising. So 5,000 is the center. So I have an array with 10,000 in it. If you hit 5,000, you're in the center. I've already worked out that this, so it basically will be in the center. So I repeat that process by changing, I got 3 baselines. So here's 1, east and west. I'll do east and north, and then I'll do west and north. And once I can confirm that all 3 baselines are generally well aligned by this FX correlation followed by inverse Fourier transform method, I can easily find out how the signals are aligned. And that's what this program does. And once I plug in new values into here iteratively, then I'll know that I'm at the right point. That when everything is at 5,000 in the center of that 10,000 point array, then I know that that I'm centered up. So this is an essential program to get kind of the coarse alignment of the data together. So then what comes next? So after this coarse alignment, and I find these numbers here, then I have another program called triple precross.py, and it is designed to just check out all three baselines all at one time to make sure they're all aligned just right. And so I took the values here from the first program, 6,592 and 296. The N channel was the lead channel, so it has a value of 0. And I plugged those values in here. And then I need to make a few little changes to see what happens. What this program does is basically the same as triple align, but since it looks at all three baselines at one time, I can confirm that all my data is truly aligned just right. So let me just run this program so you can see what it's going to do. And I'm also going to post this software along with this too, so you'll know what's going on when you actually run it yourself on your own computer. So now it's doing a calculation right now. It's going to do a baseline. All three baselines in my 3-element interferometer are going to be solved. And there we go. So here, again, this was an FX correlator, and then I did the inverse Fourier transform of that, and that gives me the signal delay values. And you can see here now I've got an array of 1,000, 500 is at the center. So if you have a peak at 500, that means your data is aligned. And let me just zoom in on that region around 500 so you can see what it looks like. So I'm stretching it out, which is something you can do with matplotlib quite easily. And you can see that I got a peak here on one of the baselines coming in at 5,001. Other baselines, there's the green, the red baselines. Their energy is spread out in several different places, pretty close to 500. And simply what this means is that the radio sky that I was observing had multiple point sources, so there is some signal delay when the object is at some different place in the sky, and you'll see some different values here. Some energy runs off a little bit further away, and by doing changes in value just very small increments, I can try to get it so that all of these peaks are as close to 500 as possible. But they cannot be entirely 500 because I have multiple sources, and they'll have different delays in the sky, so they'd be reaching the east, west, and north antennas at different times. And this could account for like a dual peak. Like there's one peak here and a peak here on the green baseline. The red baseline is complex, and the blue baseline is also complex. So this is telling me from this program that the signal alignments that I've chosen are very close, about as good as I can do for the actual large scale FX correlator that I'm going to run. So let me go ahead and close this window. I'm going to shut down this program here so we can actually look at the FX correlator. So the FX correlator is this program here. So this program